A huge thanks to Brilliant for sponsoring today's video. Today we have a classic sort of integral that is characterized by a parameter alpha. So immediately we can say that this is an integral function of the parameter alpha. And once we have integral functions like this, the first thing that comes to mind, especially when you're visiting my channel, is let's use Feynman's trick. So we're gonna differentiate I with respect to the alpha and see if we can evaluate this integral for some cool results. So differentiating the integral from 0 to infinity of e to the negative x squared plus alpha squared by x squared integration with respect to x. The first question is, can we switch up the order of the differentiation and the integration operators? Well, because you have this Gaussian sort of structure inside, it's basically a damped exponential on this interval. So yeah, there are no problems regarding convergence or boundedness, so we can perform the switch up, and once we perform the switch up, the total derivative with respect to alpha becomes a partial one. So we're differentiating partially with respect to alpha, e to the negative x squared plus alpha squared by x squared, and the integration is being carried out with respect to x. Now, because we're differentiating partially with respect to alpha, the x terms are all constants. So we have the integral from 0 to infinity of e to the negative x squared plus alpha squared by x squared. And because of the chain rule, you have this negative 2 alpha by x squared term, and we're integrating with respect to x. Next up, I want to perform a substitution going from the x world to the u world by letting alpha by x equal u. And this implies that negative alpha by x squared dx equals du. And as far as the limits are concerned, we see that as x approaches 0 from the right, u will approach infinity. And as x approaches positive infinity, u needs to approach 0. So the derivative with respect to alpha in the u world is the integral from infinity to 0 of e to the negative x squared becomes an alpha squared by u squared term, and alpha squared by x squared is u squared. Okay, cool. And we have this differential element as well, so we're only left with a factor of 2 and integration with respect to u. Now, this looks incredibly weird because we're integrating from infinity to 0, so just switch up the limits of integration so it looks nicer, and we'll introduce a negative sign. So finally, we have negative 2 times the integral from 0 to infinity of e to the negative u squared plus alpha squared by u squared du. Notice that this is exactly the same integral that we started with, the only difference being the dummy variable was x before and now it's u. So this implies that the derivative of I with respect to alpha equals negative 2 times the function I of alpha. And this is a nice first order separable differential equation. And speaking of differential equations, our sponsor for today's video, Brilliant.org, has tons of awesome STEM content ranging from algebra and everyday physics all the way up to differential equations, multivariable calculus, and quantum objects. The depth of explanation is amazing, and there are lots of exercise problems for you to test your knowledge on after learning. I especially like the interactive visuals and those application-based explanations in lessons that really help you get a grip on what you're learning. Plus, they look extremely cool and offer a fresh take by helping you visualize exactly what's going on. There are detailed explanations in case you get stuck on problems. Overall, it's a wonderful learning platform for high schoolers or university students or just anyone generally interested in math and computer science or physics. And they're adding new courses all the time, so yeah, it's worth joining. I even used it back in the day when I was learning how to code. Hold on, it gets even better. If you head on over to brilliant.org/maths505, the lucky first 200 subscribers get 20% off their annual subscriptions. I've also provided the link in the description, so what are you waiting for? Now back to our differential equation, we have di by d alpha being equal to negative 2 times I. So we can write this as 1 by I di being equal to negative 2d alpha, and integrating both sides with respect to the respective variables. So this implies that the natural log of I equals minus 2 alpha. And I know you might be thinking that we need an absolute valued sign over here, but remember, the integral I was defined as the integral from 0 to infinity, so that's the positive half of the real line of e to the negative x squared plus alpha squared by x squared dx. So we're integrating a strictly positive function here. So yeah, there is no problem here with omitting the absolute valued sign. Okay, cool. But there is a problem with missing the constant of integration, so don't do that. Okay, cool. Now exponentiating both sides, we get I being equal to e to the negative 2 alpha plus c, which can be written as e to the negative 2 alpha times e to the c, and e to the c is just another constant that we're going to call a. And now we need to determine exactly what this constant a is. And for that, we look no further than the structure of our integral. Now, accordingly, if I plug in alpha equal to 0, then I of 0 equals the integral from 0 to infinity of e to the negative x squared dx, which we all know and love as half the square root of pi. Okay, cool. So I of 0 equals 1/2 of the square root of pi, and this equals a times e to the negative 2 times 0, which is again 1. So there you go. That's your constant a. So this implies that I of alpha equals 1/2 the square root of pi times e to the negative 2 alpha. And what kind of nice result can we actually derive from here? Well, I think an obvious choice would be letting alpha be 1/4, because I 1/4 equals 1/2 the square root of pi times e to the negative 1/2, which is of course the reciprocal of the square root of e. So the integral evaluates to 1/2 of the square root of pi by e, which is another beautiful result. So I hope you enjoyed the video. Be sure to like and subscribe. Thank you. See you next time.